Hello, and welcome to Shiksha DaCosta. Today we're going to learn how to represent a quadratic situation using algebra. As part of this, we're going to create a simplified quadratic expression, and that word simplified is pretty key, that represents a situation that's in front of us. So you're successful if you can take a situation that has a quadratic relationship in it and represent it using an algebraic quadratic expression, as long as it has one variable. And if that expression is not the simplest possible one, what you're going to also be able to do by the end of this is expand and simplify it. To get our minds thinking about this in the right way, we're going to explore this idea called algebra tiles. So using algebra tiles, you're going to draw a diagram, and then you're going to express the area of that diagram, or the area of the rectangle that we will make with that diagram, that is using this algebraic expression. So what do I mean by that? If you already know how to use algebra tiles, you can go ahead and pause the video here and see if you can complete these three questions or fill in these three, and then you can resume the video when you're done. Okay, well, if you're able to do that, then fantastic. If not, well, then this is how you draw a diagram using algebra tiles. So here we have x multiplied by, in the brackets, x plus 1. So how would I draw that using algebra tiles? Well, because this is two things being multiplied, and because I know that a rectangle also is two things being multiplied, length times width, I'm going to draw a rectangle. One of these is going to represent the length, and one of them will represent the width. So for example, this is what an X algebra tile looks like. It's got a certain length, and we're not sure how long it is. It's got a width of 1. And here is another X tile. These two are the exact same in sort of length, and their width is also the same, just 1. And this is what a 1 algebra tile looks like. So in other words, this is X, and this is X plus 1. So if I were to draw a rectangle in here, the area of this rectangle would be the same thing as, to find out the area, I would just have to do x times x plus 1. And the reason we use algebra tiles is because now to find the area of this rectangle, if I made a cut along whenever there was a break, so like for example right there, I've broken it up into two shapes, and these shapes it's pretty easy to find the area of, right? So this one right here, x times x, would just be an area of x squared, and this would be 1 times x, which is just x. So the answer, what is the area of a rectangle? Using an algebraic expression, of course we don't know the actual area of this because there are unknown variables, but the area could be represented by combining these two shapes, x squared plus x. And an algebra statement would just be sort of the summary of this. X times x plus 1 is the same thing as x squared plus x. So if we take length times width, we would end up with this area, and that area is equal to the length times width itself. So this is just a brief introduction to algebra tiles, because we're going to be using algebra tiles throughout this exercise. Before we get there, though, we have one more thing that I'd like you to investigate. Using technology like Desmos, I would like you to go ahead and graph these two algebraic expressions. So you can pause the video here while you switch apps or whatever and go ahead and do that. You don't have to use Desmos. If you have a graphing calculator, that would work as well. But of course, Desmos would be the best. And once you're done, you can go ahead and resume. Okay, so hopefully you got to see that these two graphs create something like this. This is y equals x plus 4 times x plus 2, and this is y equals x squared plus 6x plus 8. What do you notice? What is your statement in mathematical notations regarding what you found out here? Hopefully you saw that, hey, this graph looks the same as this graph. Look, all the points are the same, 0, 8, 0, 8, negative 2, 0, negative 2, 0. All of these points are the same. And in fact, the mathematical statement that I make, or that I might make, is that these two, they create the same graph, so they must be equal. If these two are equal, how could we take an expression like this and turn it into an expression like this? That's what we're going to be exploring in this lesson, how to expand and simplify a quadratic expression. So the first way I'm going to take a look at doing this is going back to that minds-on activity with algebra tiles. So if I have two things being multiplied, remember that's the same thing as drawing a rectangle. One is the length, one is the width. So for example, let's say that this x plus 4, this is the width. Here's an x tile with 4 ones. And this x plus 2, that right there is our length. So we have x and then 1 and 1 here. If I were to draw a rectangle here, the area of this rectangle will be the same thing as multiplying these two. And I know that I should end up with the exact same expression as I've got here because these two are equal. How do I do that? Well, thinking back to the minds-on activity, what did we do after we made the rectangle? Well, every time there was a break, we sort of cut it up just like that. And I would do that on this side as well. And now I've broken it up into tiles that I know the area of each one. For example, this one is x times x. The area of this would be x squared. This tile down here would have a length of 1 and a width of x. And so 1 times x would be just x. This tile would be the same thing. 1 times x would be x. And each of these 4 tiles would be x times 1, which is x. Each of these tiles down here has a length of 1 and a width of 1. So these are all 1 times 1, which is just 1. So now I found the area of each individual tile in my rectangle. The total, of course, would be x squared plus x plus x plus x plus x plus x plus x plus 1 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 plus 1. Right? These were the areas of each of the separate tiles, and if we add them all together, we should get the area of the total rectangle. And in fact, doesn't that look really, really similar to something like this? Let's take a look. Well, we have x squared here, and didn't we have an x squared in our expression here? If we added all 6 of these x's up, wouldn't we get 6x? And if we added up all the 1's, well, there's 8 of them, so 8 times 1 would just be plus 8. And so in fact, yes, the multiplication of these two, the algebra tiles show us that does give us an expression that's exactly equal to this. I'm going to show that done one more way. And this time, I'm not actually going to break it into specific, 1 unit algebra tiles. I might do it a little bit faster. So for example, here, x plus 4, I have x, and then I have another length, and I'm going to say that this is 4 units. I haven't measured anything. I'm just going to say that this is 4, and for the width, or I guess this would be the width, and this is the length, it would be x plus 2. And I've just made it a little bit smaller, but this is not twice the length of this. It's just a not to scale diagram that I'm creating. The rectangle in the middle, I can still break it up along these 2 lines. And now I only have 4 tiles instead of, what was it, 15 or so to add up. Here I only have 4, which should make my job a little bit easier. So the area of this tile is x times x, which is x squared still. Okay. This tile would be 2 times x, and 2 times x is just 2x. So this has an area of 2x. This tile has an area of 4 times x, which is just 4x. And this tile has an area of 2 times 4, which is just 8. And so if I want to find the total area, that would be the same thing as doing x plus 4 times x plus 2. That would give us the area of this rectangle. The total area, I would just have to add up these 4. So x squared, I've got 2x. This one is 4x. This one is 8. And if I add these all up, well, these two are like terms. So 2x plus 4x would give me, so I've got the x squared here, 2x plus 4x does give me 6x. And how did I get 2x? I did x times 2. I took the x from the first term and I multiplied it by the 2 from the second term. This tile right here has an area of 4x, and remember how did I get that? I took the 4 from the first binomial, from the first pair, and I multiplied it by the x from the second binomial. That gave me 4x. And finally, for the 8, that's this tile right here, right? 2 plus 4 would get us 6x. So Sorry, I'm getting a little bit ahead of myself there. So if I add these together, I get 6x, and you can see that this expression is starting to come together. And of course, that 8 is the same thing as this 8, and the way I got that was I took 4 and I multiplied it by 2. I took the last two terms in each pair and I multiplied those two together. And that's how I get this expression right here. Now, there's a little sort of code to how to make this expression, to how to remember how to come up with this expression a little bit quicker. And that code is called FOIL. This means, how did we get this term? Well, I took the red and a blue x. Let's see, that's the red one, that's the blue one. These are the first two terms, and that's where we get f from. So this was achieved by multiplying the first two terms, the first term from this bracket times the first term from this bracket. How did we get 2x? We did 2 times x. These two terms were multiplied. And these are the outer two terms. These are on the outside. So that is where we get O from. How did we get 4x? Well, that was 4 times x. These are the inner two terms, and so that will have an I. And then how did we get 8? We did 4 times 2, and those were the last two terms from each bracket. 4 times 2. And that's what that code is, FOIL. So it might help you to, whenever you're multiplying two binomials, this really would help you to know, very quickly what the expression is when you actually multiply these out, which you can then simplify by collecting any like terms afterwards. Many problems in real life can be modeled using quadratics. But once the algebraic expression is created, it may look pretty complicated. It may have many terms, it may have many brackets. And when it does look like that, though, we do have to simplify it in order to work with it and make our lives a little bit easier. What does simplifying mean? It means expanding all the brackets, collecting any like terms, and then rearranging the terms so that it's in order from the highest exponent or degree to the lowest. So, for example, when you're multiplying two algebraic expressions, how do you do that? You multiply each term in the first expression by each term in the second. And if there's only two terms in each, because that's what we call a binomial. And today we only looked at binomials, expressions that have only two terms in them. And to expand binomials, it follows that exact same rule. You multiply every term in here by every term in here, and then you add that all together. With two binomials, the hint to remember it is FOIL. So F stands for first. So in this case, this would be A times C, and then O for outer two terms, A times D, I for inner two terms, that's B times C, and L for last two terms. So the last term in this bracket and the last term in this bracket, that would be B times D. And you just add these all together. If any terms end up being like terms, you can combine them at this point. And just make sure you're putting the term that has the highest exponent first, right? It always goes from highest to lowest. In this example, we're going to convert this to something called standard form. So here we have two factors. This is a quadratic relationship. It's in factored form. It doesn't look like a quadratic because there's no squared term. But we can see that if we take this and we start using FOIL, so that's 2x times 3x. O is outer two terms, so that's 2x times 2. I is inner two terms, so negative 1 times 3x. And L is the last two terms, so negative 1 times 2. Once we do that, we can see that, this is actually going to create that x squared term. We do have to add these together once we're done, right? So now that I've written out what I have to do, let's actually start to evaluate it. 2 times x times 3 times x. Well, x times x would get us x squared, and 2 times 3 would get us 6. So that would be 6x squared. 2 times x is 4x. Negative 1 times 3 times x is negative 3x, and negative 1 times 2 is negative 2. In here, these two terms both have an x in it, so they are like terms, and we can combine them by adding the number in front. So 4 plus negative 3 is just 1. And we never really write 1 when it's in front of a variable. We just write the variable itself. So that's how you do it, folks. That's how you take an expression from what's called factored form, two binomials, and expand and simplify it into something called standard form. In this example, a bus company has 12,000 passengers daily. This is an example of a quadratic relationship in real life. Each customer pays $3 whenever they're taking the bus. Now the bus company maybe wants to get some more money, so they increase the fare by 20 cents. But every time they do that, they think, okay, 1,500 of our passengers are going to say, that's too expensive for me, buddy. $3.20, no thank you. If they increase it another 20 cents, $3.40 now, another 1,500 passengers will say, no thank you, that's too expensive for me. So we're going to create an expression for the revenue of the bus company. In other words, how much money are they making? Right now, I want you to pause it and see if you can figure out how much money they're making right now before they do any fare increases. If your answer was 36,000, you are absolutely correct, right? 12,000 passengers per day, each paying $3 would be $3 times 12,000. That's what revenue is, how much money this company is making. Now, what is the variable in this situation? What can change? It looks like they are increasing the price, so they're increasing the fare, and they may do that again and again and again. So it says for each time they do that. So I think in this case, the variable is the number of times that they change the price, the number of price increases. Whenever you're modeling a situation, you always want to make a let statement where you define what the variable actually represents. So in this case, how do we calculate the fare? Well, it's $3 right now, but every time they increase the price, we will need to add 0.2. So it'd be $3 plus 20 cents times the number of price increases. If they increase it twice, that would be 20 cents times 2, which is 40 cents. If they increase it 10 times, that's an extra $2, 20 cents times 10. So that's the fare. But the number of passengers will change as well every time they increase the price. So the number of passengers will go down. So notice I have subtraction by 1,500. And that's for every price increase, for each one. So if I increase the price twice, then I will lose 3,000 customers. So I will have to subtract 3,000. So I'm going to take this pink part and replace fare with this expression, and I'm going to replace the number of passengers with this expression, and that is how I calculate revenue. Now, this question has a very important key word. It has what I needed to do was create a simplified algebraic expression, not just any one. And this is not simplified because I still see some brackets going on here. So how do we make this expression simplified? We just use FOIL. So go ahead and try that yourself. Pause the video here, and once you're done, you can go ahead and hit resume and see if you got it right. So FOIL, let's see if your answer is correct. F is the first two terms, 3 times 12,000. O is the outer two terms, 3 times negative 1,500x. I is the inner two terms, 0.2x times 12,000. And L is the last two terms, 0.2x times negative 1,500x. And then we have to add all these together. So what do we get? 36,000 minus 45,000, because we're adding a negative. This will end up being a negative number. Plus 2,400x minus 300x squared. X times x would have gotten us x squared. Now notice that these two terms in the middle both have an x. Those are like terms. This is just a number, and this is x squared, so they're not like each other. But these two I can add. Negative 4,500 plus 2,400 would give me negative 2,100. Notice I also took this negative 300x squared and I moved it in front, and I took the 36,000 and I moved it in the back so that it's going from the highest exponent to the lowest. This is x to the power of 1, and this is actually, it's not written here, but it's x to the power of 0, which is equal to 1. So 36,000 times 1. This is why we don't write anything to the power of 0. And that's the equation for a simplified algebraic expression for the revenue of this bus company, depending on how many times they increase the price. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.